Hi guys, so this is Vicky continuing with the 2014 FRQ question number 4. So here we see that there's calcium carbonate becoming calcium oxide and carbon dioxide. When heated, calcium carbonate decomposes according to the equation above. In a study of the decomposition of calcium carbonate, a student added 50-gram sample of powder CaCO3 to a 1 liter rigid container. The student sealed the container, pumped out all the gases, then heated the container in an oven at 1100 Kelvin. As the container was heated, the total pressure of CO2 in the container was measured over time. The data are plotted in the graph below. So it says, the student repeated the experiment, but this time the student used a 100-gram sample of powdered CaCO3. In this experiment, the final pressure in the container was 1.04 atmospheres, which was the same final pressure as in the first experiment. Calculate number of moles of CO2 represented in the container after 20 minutes. All right, so this is just purely the ideal gas law, okay? So they tell you that the container is rigid. They tell you that the gases are ideal. So let's just use PV equals nRT. And what is pressure here? Pressure happens to be 1.04, right? So that's 1.04 atmospheres. What is the volume? It's 1 liter is equal to N number of moles. And R is a gas constant, 0.0821 liters atmospheres over moles of Kelvin. Okay, and what is the temperature, guys? The temperature is right here. It's 1100 Kelvin. And if you do the math, you end up with 0.0115 moles of CO2. And that's it. Super easy, right? All right, let's continue with B. B says the student claimed that the final pressure in the container in each experiment became constant because all of the CaCO3 had decomposed. Based on the data in the experiments, do you agree with this claim? So they're saying that the final pressure in the container in each experiment became constant. No, because here's the thing. We don't agree. Do not agree, because here's one of the explanations. The explanation is basically saying that CaCO3, we had 50 grams of it, right? And what is 50 grams? So CaCO3, CaO plus CO2. So if I have 50 grams of this, if I were to switch it to moles, right, I end up with 0.5 moles of this, right? But how many moles of CO2 did I end up with? I ended up with 0.0115 moles. So is that true? Is it true that the final pressure are consistent? No, because if the moles change, then the pressure changes due to PV equals nRT, right? So that's false. So let's look at a different argument. A different argument would be that the experiments are two different experiments, because one we started out with 50 grams and then the other one started out with 100 grams, right? So if we start out with two different masses, we end up with, if I have 50 grams of this, that's 0.5 moles of CaCO3, versus if I have 100 grams of this, that's like what? Closer to 1 mole, right? So the number of moles of CaCO3 changed. So obviously due to PV equals nRT, if the moles changes, the pressure is bound to change. Okay? All right, let's continue with C. And what does C say? It says after 20 minutes, some CO2 was injected into the container, initially raising the pressure to 1.5. Would the final pressure inside the container be less than, greater than, or equal to 1.04? So what did they say? The final temperature, the final pressure. They're saying the final pressure, and look what happened at the final pressure. It always equilibrates out, right? So based on the fact that this is reaching equilibrium, it doesn't matter if your initial was 1.5 at the end or at equilibrium, you will end up with 1.04 atmospheres. Okay, so nothing changes. Nothing changes because we just reached equilibrium. Okie dokies? All right, let's continue to D. D says, are there sufficient data obtained in experiment to determine the value of equilibrium constant Kp for the decomposition of CaCO3? Justify your answer. Yes, we do. Why? Because what is Kp? Kp is products over reactants, the pressure of products over reactants. And look at the equation. But if I were to go back and I look at this equation right here, the thing is, because that's a solid, we don't include it into a K equilibrium. That's also a solid. We don't include it into the K equilibrium. The only one that we include is the CO2. So that's partial pressure of CO2 over 1. So whatever the partial pressure of CO2 it is at equilibrium, which is 1.04 atmospheres at equilibrium, that is Kp. And remember, Kp, because it's part of the K equilibrium, there is no units. And that's it. Hope you guys enjoyed it. See you guys later.